Okay, let's talk about cylindrical shells. And the reason we need cylindrical shells is because there are going to be scenarios in which washers won't do the trick for us. It's not going to be possible to find the volume of a three-dimensional shape using the washer method, so we need shells. And I know some people don't really like shells, but I really do think they're the superior method in terms of thinking about how things work in other fields. We don't use a lot of cylindrical shells in physics, but we use a lot of spherical shells, and the idea is the same. So let's talk through this idea. And the pictures are even more difficult than washers, but in general, what does a shell look like? And what's the volume of it? So all of these kind of go down to the fact that we're looking at some circle, and it really is kind of a ring here, and then we're going to give it a height, and so then it's this cylindrical shell. Okay, and so then what's the volume of this guy? Well, the volume of each one of these things is going to be the perimeter, right? This distance around, this thickness, which is going to be dx, and this height. Dx or dy just kind of depends. Okay, and really that's kind of a dv, because it's the individual volume of each one of these things, and then the total volume, v, would be the accumulation of each one of those little bitty volumes, 2 pi r h dx or dy. Again, this is the formula that we're going to use on all these guys. And all you have to do is find the limits, which is pretty easy, and then establish h and r. And they have to get established very similar to how you do everything else. Just draw a picture and then think about what r is and what h is, and then slap them in there and you're done. So I don't really think cylindrical shells are really that bad. Again, the theory says that we're going to take this, and let's do this one, and I might even draw this twice. Let's take this and let's revolve it around the line. Oh, let's just revolve it around the y-axis. Okay, so let's say we didn't know about shells, or we didn't believe in shells. We're like, all right, let's just do washers. So how do you do washers? Well, you take from your axis, you go out to here, and then you go to the short curve. So that's big R, and that's little r, and you're like, oh, well, I need to solve this. So it's like, oh man, it's the same curve here and here. How does that actually, wait a second, washers isn't going to work. Okay, and so when do you use shells? Well, you use shells when washers don't work, and the more practice you do, you'll realize right away that shells is the go-to thing here, and shells will end up being really easy. So I'll just draw that again. There's the sine curve, and we want to revolve it around this line. Okay, and so here's the cylindrical shell idea. So the height, h, always parallel to the axis of rotation. Okay, and so I'm going to attempt to draw just one of these for you. Okay, so here's the height. That's h. Do you see how that's got a thickness already of dx? And then we're going to rotate it around this. We're going to do something that would look like that. Okay, so we take this entire shape and we keep whipping around different things. If I draw more on there, it'll just get worse. But that's just one of the cylindrical shells. And we get, you know, one over here is a little smaller, but it's a little wider. And you stack all those shells up, well, then you get the same shape as you would have always gotten. It's this weird donut shape that's got this little weird, you know, tornado cut out of the middle. Okay, and so the formula is right there. So the volume of this guy is equal to what? Integral from what to what? Well, this is pi, comma 0. So we're going to go from 0 to pi, 2 pi r, right? 2 pi r h. What's r? Well, r is this distance. Right, this is in red. Think about it. Look at the cylinder, man. What's the radius of the cylinder? It's just the x value, right? This is the height. I'm taking this solid piece right here. The height is always parallel to the axis. Axis parallels the height. That's the height. Look at the height's got a thickness of dx, right? A width of dx, and then I'm whipping it around here. Well, this distance from the axis to this piece here is just straight up x. So 2 pi x is our r, And then what's our h? Well, h is just the curve, sine x in this case, and the thickness dx. Look how easy that is. 2 pi r h dx. Slap that all together and you get 2 pi. Okay, so this is the formula, but the formula is just building up the volume of what you know a cylindrical shell is. And again, it's a shell. It's not a whole cylinder because it's only going to thickness dx in this case. So do this one. Again, let's take this and let's revolve it around this guy. We did this exact same problem using washers. With washers, we went boom, and we had to solve this for x and solve this for x. Watch how fast cylindrical shells are. First thing is draw the height. The height is parallel to the axis. So just take one example and draw the height. There's h. You can remind yourself it has thickness dx, and then go from your axis to that curve, and that's your r value. And then the volume is just the integral from, again, this point here. This was 2, 8, 0 to 2 pi. All right, what's r? What's this distance? Well, this distance is just x, and this is 4. So x plus 4 is r. And then what's this height curve? Well, the height curve is the difference between this curve and this curve. So h is just 4x minus x cubed dx. Slap them together. Again, I'll draw one now that I'm over with. I'll draw one so in case I mess it up. So something like this. Whip that around. So that's that cylindrical shell for that little one, right? We're taking this solid piece and whipping around that axis. And it's going to form a shape that looks like that. And if you do that for all of these different segments, right, take one in here and whip it around. And it's going to be that one. You stack all things together and you get whatever that shape ends up being. Right? The answer, what is that? Well, it's the same answer as we got on the old, whoa buddy, 608 over 15 pi. And you can compare the videos to show that this using washers and using cylindrical shells, of course, is the same volume because it's the same shape. You're taking the same area around the same axis. Of course, it's the same shape. You're just solving it in a different way. Okay, let's take this one. And what are we going to do with this one? Let's revolve this one around the line x equals 2. So it's over here. No big deal. Same thing. Draw the height. There's the height. H. It's got thickness, dx. Go from your axis of rotation to one of them. That's our volume. Accumulate 2 pi r. All right, take a breath. What's r? From here to here is the x value of that particular point. From here to here is 2. So, as always, right curve minus left curve. So the radius is 2 minus x. Think that through again. This from here to the shell is x. From here to here is 2. So 2 minus x gives you that. And then what's the height? Well, the height's just the curve. That's easy. This is another example, like this example, where washers would not work. If you try to do washers, you'd have to do big R, little r, and you're like, oh man, big R and little r are the same function. How do you solve this for x? Yeah, good luck with that. Can't do it. So you have to do cylindrical shells. These are two examples where you have to do shells. This is an example where I think cylindrical shells are easier, but you could have done washers. Okay, again, 2 pi r h dx. In this case, we're going to do 2 pi r h dy. Okay, let's take this and let's revolve it around y equals -2. Again, what did I say? The first thing you should do if you're going to try to do cylindrical shells, draw the height parallel to the axis. That's h. And just look at it. What's the thickness? dy. You already know you're in y's. And again, it's kind of a hint at the fact that I gave you x equals in terms of y. And then draw the radius. Go from your axis up to that one shell. That's r. And then the volume is the accumulation of all these cylindrical shells. 2 pi r. What's r? Well, this, the height of that shell above the axis is just a y value. So it's y plus 2. Y plus 2. And then the height is this distance. Well, that's just straight up the curve. Right? X equals, they've already solved for x, which is nice. Y minus y squared dy. dy, all y's. Y limits. Right? All right, that's 0, 0. And then probably not too much work to figure out that that's 1 comma, or excuse me, 0 comma 1. Right, when you plug in 1 for y, you get 0 for x. So we want to integrate from 0 to 1. I didn't actually say what we integrated over here from. We integrated dx, so we're going to go from 0 to 1. The intersection here is 1 comma 0. These are kind of just flipped examples of each other. 1 to 0. And this volume, did I do this one? Let me give it a little look here. Yeah, I think I did. Pi over 2 is the volume of that guy if you were working them through. And then over here, you get 5/6 pi. And again, if you want to try to draw one of them on each one of these, feel free. It doesn't matter to me. But I think the important thing is draw the curve, find the intersection, draw a dotted line for the axis, draw the height, which is always parallel to the axis, draw the radius, which is literally the radius of the cylinder you would draw, and then you can see the thickness of the height is dx, so you know you're in x's, x limits, x functions. And again, if you tried to draw one of these, right, it's going to go like way over to here. That and that. Right, that's that particular cylindrical shell. Right? You're highlighting this and you're whipping that little post around and forming this. And again, its volume is 2 pi RH. And again, just draw H, R, find equations for H and R, and then do the integral. And again, your calculator is going to do most of these integrals for you. This one, the cylinder would run something like that. Right, you're taking this guy and whipping around this axis, and you get some cylindrical shell, and you're adding them up, and you can see the thickness of the shell is dy, the height is going to be an x value, right? X equals stuff with y's, and then r, in this case, it's y plus a 2, right? Top minus bottom, y minus a minus 2 gives you y plus 2. Okay, so hopefully this gave you a kind of a good overview of cylindrical shells. I think this is the key. Draw that first, then draw R. Again, R, start at your axis and go all the way to your to the height you drew. And again, if you look at this, this one was just x. This was x plus 4 because I shifted it that way. This was 2 minus x because I shifted it to the right, similar to washer stuff. And this one was a y value plus 2 was r. H in this case was a top. This was a top minus a bottom. This was just the top because there's no bottom. And then this was just the right, but it could have been right minus left. And again, it's just a horizontal distance. Okay, hopefully you've watched all 3 of the videos on volume, discs, washers, and shells. And you can compare all 3 and know when to apply each three of the things.